I want you to think back,
Yeah.
actually, really try to picture it. Think about your absolute earliest memories. Try to picture your oldest, most comforting childhood blanket.
Oh, yeah. Or, maybe it wasn't even a blanket. For a lot of us, it was a specific, incredibly soft, probably totally disintegrating cloth diaper or something.
Right. Or a stuffed animal that you just dragged around everywhere through the dirt. You know the exact piece of fabric I'm talking about.
Oh, absolutely. The one your parents desperately tried to sneak into the washing machine while you were asleep.
Exactly. Which usually resulted in an absolute meltdown when you woke up and found your primary source of comfort missing.
It's funny, but it's a practically universal human experience.
Mm.
And professional psychologists actually have a specific clinical term for this, um, this beloved grubby piece of fabric. They call it a transitional object.
A transitional object, like it transitions you from being totally dependent on your parents.
Essentially, yes. The underlying theory in developmental psychology is that this intense attachment is the infant's attempt to evoke maternal comfort when the mother isn't immediately present.
Oh, wow. So they're using the cloth as a stand-in.
Right. The child is creating a physical proxy. Cloth, or something similarly soft and fuzzy, is our very first, almost inevitable infantile symbol of maternal security. Because, touch comes through those blankets from literally the moment of birth.
That is so fascinating. And welcome, everyone. I'm your host, and joining me today is our resident expert to guide us through this. Today, we're looking at a really diverse stack of sources for this deep dive.
Yeah, we've got everything from dense textile engineering textbooks and historical supply chain audits to consumer protection data and environmental impact report.
It's a huge pile of information. But the common thread, pun totally intended there, across all this material is how fundamentally disconnected we are from this material that we literally wrap ourselves in 24/7.
It's so true. And I love that psychological framing from the research you just mentioned. We are handed a piece of fabric the second we are born. It's our first tactile experience of the outside world.
Yeah, the infant takes this mundane bit of cloth and conceptually transforms it,
Yeah.
investing it with the psychological power to satisfy a deep longing for security. It's wild.
And that profound connection doesn't simply evaporate when we grow up and throw away the baby blanket.
Yeah.
In our adult lives, cloth continues to play intertwined aesthetic and functional roles that we, rarely stop to analyze.
No, we don't. But think about it. Textiles, from intricate oriental rugs to heavy draperies down to just a really thick, well-made bath towel, they're arguably the primary source of domestic beauty in our homes.
Right, and they provide physical protection in a way nothing else in architecture can. A house has hard walls and glass windows, but textiles shield us from the glare of the light.
Yeah, they dampen acoustic echoes, they insulate against drafts, and they protect us from the hard, abrasive surfaces of our own furniture.
Exactly. The emotional warmth of a home depends heavily on the unconscious resonance of the sensations aroused by fabrics. Think about sliding into cool, crisp sheets at the end of a long day.
Oh, the best feeling. Or walking barefoot across a really deep pile carpet.
Yeah, and through intricate chains of memory and association, those adult tactile experiences link all the way back to those primordial feelings of safety and warmth we first experienced through cloth.
Which really brings us to the core problem here and the mission of today's deep dive. We interact with cloth 24 hours a day. We never take it off except to bathe or to change into other cloth.
Right, it's constant.
Yet reading through these textile engineering texts, I realized I know absolutely nothing about it. The material argues that we are what they call unconscious connoisseurs.
Unconscious connoisseurs. I love that phrase. It means we know what feels good, right? But for a variety of historical reasons, the modern consumer knows far less about the actual mechanics, production, and care of textiles than a person living just 100 years ago.
Why is that, though? How did we lose that knowledge?
Well, we operate in a state of diminished understanding, mainly due to our distance from the manufacturing process. A century ago, people were intimately familiar with the loom, the spinning wheel, or at least the raw fibers.
Because garments were often made or heavily repaired right in the home?
Exactly. Today, we simply order finished garments online and they show up in a bag. But, we shouldn't place all the blame on the modern consumer. The sheer volume of technical knowledge required to understand modern textiles has expanded exponentially.
It really has. The historical timeline in our sources maps out this absolute labyrinth of modern fibers. Up until the late 19th century, if you lived in the Western world, your entire textile reality was super restricted.
Very restricted. You only had about 4 or 5 natural fibers to choose from.
Yeah, even fast forwarding to 1940, A typical household only had to manage fabrics made from about 6 basic fibers. You had silk, linen, cotton, and wool.
And then you had rayon, which is a cellulosic fiber drawn from wood pulp, and acetate. But that was it, 6 fibers.
That is a totally manageable mental load for a consumer trying to figure out how to do the laundry, right? But then something changed.
Right, the inflection point hits around 1960. In the span of just 2 decades post-World War II, the chemical industry pivoted from wartime production to consumer goods.
And the textile market was suddenly flooded with completely synthetic fibers.
Exactly. We see the mass introduction of nylons, acrylics, modacrylics, olefins, and polyesters. And it didn't stop with just the extrusion of raw plastics into thread.
No, the industry developed this explosion of chemical and mechanical finishing treatments to force these materials to behave in unnatural ways. The documentation points to this relentless pursuit of miracle fabrics by mid-century chemical companies.
Oh, absolutely. The post-war consumer wanted clothing that performed impossible feats. They demanded permanent water repellency, enhanced flame resistance.
Fabrics that violently resisted shrinking. And above all, the holy grail of mid-century domestic life. Clothes that never had to be ironed.
Right, the permanent press. They achieved many of those functional goals through complex chemical engineering, but the unintended consequence was a total severing of the consumer's intuitive understanding of the material.
Because you couldn't trust your hands anymore. By combining multiple synthetic and natural fibers into complex blends and coating them in chemical finishes, the true identity of the fabric became disguised.
Disguised is the perfect word. Today, not even a seasoned textile professional can definitively discern the composition or the required care of a modern fabric simply by touching it or looking at it. The tactile feedback loop has literally been broken by chemistry.
So, to solve the ensuing chaos in the laundry room, the government intervened. The Federal Trade Commission introduced the care labeling rule.
Ah, yes, the care labeling rule. They mandated those little, often incredibly itchy tags attached to the back seam of your shirts.
Manufacturers are legally required to provide fiber content labels specifying the exact percentages by weight, like 60% cotton, 40% polyester, along with specific instructions for washing, drying, and ironing.
The mandated labels are a baseline consumer protection, sure. But the engineering sources we are reviewing highlight massive structural flaws in relying entirely on them.
Yeah, like first off, the care information is exceedingly limited. Second, compliance and accuracy are just not guaranteed.
Right, mistakes occur in mass manufacturing, obviously. But more importantly, incorrect labeling is frequently intentional.
This part blew my mind. The textbook introduces a concept called low labeling, and it completely changed how I view my closet.
Low labeling is fascinating. It's when a manufacturer deliberately recommends a care treatment that is far more conservative and usually far more expensive than what the fabric actually requires.
Yeah, like when they stamp dry clean only on a sweater that could easily survive a gentle hand wash in the sink. Why do they do that?
The motivation is purely liability management. By dictating the gentlest, most controlled cleaning method possible, which is commercial dry cleaning, the manufacturer minimizes the risk that the consumer will shrink or ruin the garment in a hot washing machine and demand a refund.
It reminds me of the best by dates on fresh produce. The date on a bag of spinach isn't a magical expiration clock, It's just the producer guaranteeing peak aesthetic quality and covering themselves against complaints.
That's a perfect analogy. But consumers treat that date as a hard rule and throw perfectly good food in the trash.
Exactly. And with clothing, low labeling limits our ability to care for our own belongings economically. If you follow a dry clean only label on a low-labeled cotton blend shirt, you're exposing your clothes to harsh industrial solvents and spending absurd amounts of money to mitigate a risk the manufacturer just didn't want to take.
Furthermore, even when a care label is perfectly honest, it fails to educate the consumer because it lacks context.
What do you mean by context?
Well, a label provides an imperative command, right? Like, do not use bleach. But it completely omits the physical or chemical rationale. Without knowing why you shouldn't use bleach, you can't make an informed decision.
Oh, I see. Like, will the bleach physically dissolve the structural integrity of the spandex in the blend? Or will it merely cause a synthetic fiber to yellow slightly?
Exactly. If you don't understand the underlying chemistry, you are just blindly following orders.
And that's assuming the label is even there. Our sources point out a massive loophole in the regulations regarding household furnishings.
Oh yeah, the law currently does not require care labels on items like custom draperies, tapestries, or certain types of heavy upholstery.
Which is crazy. You could invest thousands of dollars in living room textiles and receive zero guidance on how to actually maintain them.
Which is why relying on the fiber content percentage, knowing it's 60% cotton and 40% polyester, is supposed to be the consumer's backup plan. If you understand the raw properties of polyester, you should theoretically know how the fabric will behave regarding heat, abrasion, and moisture.
But the research clearly shows that knowing the fiber content is only the first variable in a very complex equation. Because you can have two fabrics made of the exact same 100% cotton fiber, and one will be a delicate sheer material that tears easily, while the other is a rugged pair of denim jeans.
Right. The raw material is the same. The difference lies entirely in the physical construction. To read the fabric of our homes, we really have to understand textile architecture, starting with the two grand classifications: weaving versus knitting.
Let's get into that. This structural divide determines almost everything about how a fabric drapes, stretches, and survives wear. Woven fabrics are constructed by interlacing yarns. Knitted fabrics are constructed by interlooping yarns.
Let's examine weaving first, as it is the older and, generally speaking, more structurally stable method. Woven fabrics are produced on a loom.
Okay, picture a loom. You have a set of lengthwise threads known as the warp yarns, which are held under high tension.
And then you have the crosswise yarns, known as the filling yarns, or the reft, which are interlaced over and under the warp yarns.
Before we get into the specific patterns of that over-under interlacing, though, we absolutely have to address a marketing metric that the textile industry has weaponized against consumers.
Let me guess. Thread count.
Thread count. When you walk into a department store to buy sheets, 1,000 thread count is plastered across the packaging in massive font. We've been thoroughly conditioned to equate a higher number with superior luxury and durability.
Oh, totally. But the engineering textbook essentially calls this a localized scam.
It really does.
Yeah.
Is thread count just the textile equivalent of megapixels on a digital camera? Marketers convince us a 20-megapixel camera is automatically better than a 12-megapixel one, ignoring the fact that if the lens is made of cheap plastic, the resulting photo will still be terrible.
The megapixel analogy is highly appropriate here. Thread count, which textile engineers actually refer to as fabric count, is simply a measure of density. It counts the number of warp yarns and filling yarns packed into 1 square inch of fabric.
So it's just a single data point stripped of all structural context.
Exactly. The true durability and quality of a cloth depend on the weight of the fabric, the raw quality of the fiber, the twist of the yarn, and the geometry of the weave.
So packing more threads into an inch doesn't magically make the fabric stronger. If a manufacturer achieves 1,000 thread count by using incredibly fragile microscopic yarns, compressing them together, that sheet will tear much faster than a 300 thread count sheet woven with robust, high-quality yarns.
It's exactly the opposite of what the marketing implies. The source text provides a really stark example. Compare a pair of heavy-duty cotton work pants, like denim, with a luxury sateen sheet made of combed Egyptian cotton boasting a thread count of 300.
The denim has a significantly lower thread count because the individual yarns are physically thicker, right? You simply cannot fit as many of them into a square inch.
Right. Yet the denim will survive years of harsh abrasion, while the high thread count sateen will wear through relatively quickly under similar stress.
The engineering documents also break down how this metric is manipulated. Fabric count is usually expressed as two numbers, like 64 by 60. That means 64 warp yarns running vertically and 60 filling yarns running horizontally per inch.
But sheet manufacturers combine those numbers to produce one large, impressive figure for the packaging, hence a 120 thread count sheet.
And they typically do this with balanced fabrics, where the number of warp and weft yarns are roughly equal. Why is balance so important?
Balance is far more critical to durability than the raw numerical count. In a balanced construction, where the warp and filling yarns are of similar size and density, the physical stress of pulling and rubbing is distributed evenly across all the structural elements.
Ah, okay. So if a fabric has a highly unbalanced construction, say 120 warp yarns but only 40 filling yarns, what happens?
The physical properties degrade. The tighter, more numerous warp yarns will bear the brunt of any abrasion, causing the fabric to split vertically much faster. An authority cited in the text explicitly states that a fabric with a lower thread count but excellent balance will outwear a fabric with a high thread count but poor balance.
That is so good to know next time you're shopping. So assuming we have well-balanced yarns, how those yarns actually intersect is what creates the distinct types of cloth we see in our closets.
Right, and the sources categorize almost all woven fabrics into 3 foundational patterns: plain weave, Twill weave and satin weave. Let's start with the plain weave. It is the most fundamental geometry.
It's a strict alternating pattern, right? The filling yarn goes over one warp yarn, under the next, over the next, across the entire width.
Yes, and on the return pass, the pattern reverses. This creates a microscopic checkerboard structure. Because it is perfectly symmetrical, a plain weave fabric looks identical on both the face and the back.
And it's incredibly common. Broadcloth, percale sheets, tweed, and muslin are all plain weaves. When woven tightly, it is highly durable because there are maximum intersections locking the yarns in place.
But there's a big but here. The textbook notes a major functional flaw. Plain weave fabrics are structurally prone to wrinkling.
Because the yarns are locked so tightly in that over-under grid, when the fabric is crushed, the yarns can't slide past each other to absorb the distortion. They basically bend, and the fabric holds the crease.
Exactly. There are variations to manipulate these properties, though. Take the basket weave, used in Oxford cloth. It groups yarns together. Instead of one over, one under, you might have two filling yarns weaving over and under two warp yarns simultaneously.
And this looser interlacing creates a softer, more flexible fabric that drapes better and resists wrinkling slightly more than a tight plain weave.
Yes. However, the reduction in intersections means the yarns can shift more easily, decreasing the fabric's overall durability and making it much more prone to snagging.
Another plain weave variation is the ribbed weave, like poplin or taffeta. They create this by using filling yarns that are physically much thicker than the warp yarns, which creates pronounced horizontal ridges across the fabric.
It looks elegant, but the physics of those ridges creates a wear and tear nightmare.
Oh, I bet. Every time that fabric rubs against a chair, the raised, thick yarn takes 100% of the abrasive friction.
It acts like a speed bump. It wears down quickly while the recessed warp yarns remain untouched. So, to solve the issues of durability and wrinkling inherent in the plain weave, engineers developed the twill weave.
Visually, a twill is immediately recognizable by the diagonal lines running across the surface of the fabric. Structurally, instead of going over one and under one, a filling yarn in a twill will float over 2 or 3 warp yarns before going under.
And crucially, with each successive horizontal row, the point of intersection shifts over by one warp yarn. This systematic shifting is what generates the diagonal line, or wale.
I looked at my jeans while reading this section, and you can see that diagonal line clear as day. Denim is a twill. Suits, heavy coats, gabardine, they all rely on this construction. But why does floating a yarn over multiple other yarns make it stronger than the tightly locked plain weave?
It comes down to density and flexibility. Because the yarns in a twill are interlaced less frequently than in a plain weave, they can be packed together much more tightly.
Oh, so you can jam more heavy yarns into the same square inch, creating a thicker, heavier, more robust material.
Precisely. Furthermore, those slightly longer floats give the yarns room to move and shift when the fabric is bent or crushed. This structural mobility allows twill fabrics to resist wrinkling far better than plain weaves and to drape more heavily.
The third foundational category is the satin weave, which completely prioritizes aesthetics over durability. The goal of a satin weave is to create an unbroken, smooth, highly reflective surface.
To achieve this, the warp yarns are allowed to float over 4, 5, or even up to 11 filling yarns before finally dipping under one to anchor the structure.
11 filling yarns. That's a huge gap. So by minimizing the interlacing points, the surface of the fabric becomes dominated by long, exposed, parallel lengths of yarn.
And when light hits these uninterrupted floats, it reflects smoothly, generating the characteristic high luster and shine we associate with satin.
But those long, shiny floats are a massive structural liability. Satin is notorious for snagging. If you brush a satin dress against a rough piece of wood, that exposed millimeter of floating yarn easily catches, pulls, and ruins the smooth surface.
The engineers know that to compensate for this fragility, satin weaves are packed incredibly densely, which actually makes them surprisingly warm and heavy, but they will never withstand the abrasion that a twill weave can handle.
So plain, twill, and satin form the basics. But the historical documentation delves into the evolution of complex weaves, which represents a massive leap in human engineering. Complex patterns like damask or brocade require the individual manipulation of thousands of specific warp yarns to weave intricate, non-repeating floral or geometric designs.
And doing that by hand was agonizingly slow. Originally, they used draw boys, actual children sitting atop the loom, manually pulling specific clusters of threads based on instructions from the weaver below.
Wait, actual children sitting on the machine?
Yeah, it was incredibly dangerous and slow. But then, in 1804, Joseph Marie Jacquard invented a mechanical module that attached to the loom.
And the source material draws a direct, undeniable line between the Jacquard loom and the birth of modern computing.
Mm.
Can you break down the mechanics of how this loom actually worked? Because this was a mind-blowing moment in the text for me.
It really is. So the Jacquard mechanism replaced the human drawboy with a system of heavy, interchangeable punched cards. Imagine a continuous chain of stiff cardboard cards feeding into the top of the loom.
Okay, I'm picturing it.
Each card represents one horizontal pass of the weaving shuttle. The card is punched with a specific pattern of holes. Inside the mechanism, there is an array of spring-loaded needles, each connected to a hook that controls a single warp yarn.
So when the mechanism presses the card against the array of needles, it acts as a physical binary system.
Exactly. If a needle hits solid cardboard representing a 0, it is pushed back, the hook disengages, and that specific warp yarn stays down.
And if a needle finds a punched hole representing a 1, it passes through, the hook engages, and the machine lifts that specific warp yarn up.
Yes. By simply changing the sequence of the punched cards, a weaver could automatically produce infinitely complex patterns. Charles Babbage later observed this binary punch card system and adapted it for his analytical engine, laying the theoretical groundwork for computer programming.
That is insane. When you look at a piece of heavy jacquard upholstery, you're looking at the physical output of the world's first digital code.
It's incredible that the structural logic of a decorative fabric directly birthed the information age. But weaving, no matter how complex the binary code, is still based on interlacing straight lines under tension.
Right, which the text contrasts completely with the second major architecture of cloth, knits.
Knitted fabrics are formed by a continuous interlooping of yarns. Rather than straight warp and weft yarns crossing over each other, a knitting machine creates a row of loops and then pulls a new row of loops through the previous ones.
And this fundamental geometric shift from straight lines to curves changes everything about the physical properties of the material, the primary property being elasticity.
Oh yes. Woven fabrics are generally rigid, they have structural stability, but the loops in a knit fabric can stretch and distort in multiple directions when pulled and then snap back into shape.
Which makes knits unparalleled for comfort and fit. They mold to the body. They are also virtually immune to wrinkling because the looping structure acts like a series of microscopic springs that absorb the crush of being folded or packed in a suitcase.
However, that inherent elasticity creates significant vulnerabilities. Knits are fundamentally less stable than weaves. If they are constructed loosely or with low-quality yarns, they suffer from bagging, they stretch out at the knees or elbows and lose their structural memory.
Oh, I hate when that happens to a sweater.
Yeah.
They're also highly susceptible to shrinking when exposed to the heat and agitation of a washing machine, right? As the loops contract and tighten.
Exactly. Now, the mechanical analysis of knits divides them into two distinct production methods, weft knitting and warp knitting. Weft knitting is the mechanical equivalent of what a person does with two knitting needles.
A single yarn travels horizontally, back and forth across the width of the fabric, forming loops row by row.
Right. Weft knits include the plain knit, universally known in clothing as jersey. Jersey has immense crosswise stretch, which is why it is the standard for t-shirts and underwear.
But it has a fatal mechanical flaw inherent to its continuous horizontal yarn structure. If a single yarn breaks, the loop releases the loop below it, causing a vertical run or ladder that rapidly unravels the fabric.
We've all seen a run in a stocking or a snag in a t-shirt do that. The other common weft knit is the rib knit. By alternating knit and purl stitches vertically, the machine creates a fabric with deep longitudinal ridges.
Rib knits have massive, aggressive, crosswise elasticity. They are engineered to stretch wide over a head or a hand and then contract forcefully, making them the structural choice for the cuffs and collars of sweaters.
To combat the unraveling problem of weft knits, the industry utilizes warp knitting. In a warp knit, the yarns do not travel horizontally.
Right. Instead, hundreds of parallel yarns travel vertically down the length of the fabric, zigzagging and interlooping with adjacent yarns simultaneously.
The structural advantage here is security. Because the loops are interlocked diagonally across multiple vertical columns, a broken yarn cannot trigger a cascading failure. Warp knits will not run.
Tricot, heavily used in lightweight lingerie, is a warp knit. The engineering is so precise that modern racial warp knitting machines can produce complex, heavy blankets or mimic the most delicate, intricate lace that used to take human artisans months to weave by hand.
Okay, so we've mapped the architecture of the cloth, the straight line grid of the weaves, and the spring-like loops of the knits. But the foundational building block of both systems is the yarn itself.
Yeah, if the weave is the blueprint, the yarn is the brick. And the textbook dedicates a massive section to unraveling these yarns to see how their internal construction alters the final fabric.
The construction of a yarn depends entirely on the physical dimensions of the raw fiber being used. In the textile industry, all raw fibers are classified into two categories based on length: staple fibers and filament fibers.
Let's break those down. Staple fibers are relatively short, naturally occurring lengths. Cotton bolls produce fibers that are barely an inch long. Wool shorn from a sheep consists of fibers a few inches long.
Flax for linen is slightly longer, but still limited. To create a continuous, usable yarn from these thousands of tiny, separate fibers, they must be aligned and twisted together in a process called spinning.
And the preparation of those staple fibers before they are spun dictates the smoothness and strength of the final yarn. When raw cotton or wool is processed, it first goes through carding.
Right, a carding machine uses massive drums covered in fine wire teeth to aggressively tear apart the clumps of raw material, remove debris, and roughly align the fibers into a loose, continuous rope called a sliver.
But a yarn spun directly from this carded sliver is functional, but it contains a chaotic mix of long fibers and short, stubby, weak fibers all twisted together. The resulting yarn is fuzzy, uneven, and prone to breaking.
So to produce high-quality staple yarn, the manufacturer must put the carded sliver through an expensive secondary process called combing.
Which literally acts like a fine-tooth comb pulling through hair, right? This machine aligns the fibers perfectly parallel to one another. Crucially, the combing mechanism physically rejects and extracts all the short, inferior fibers.
This is a major practical takeaway for anyone buying clothes. When a label specifies 100% combed cotton, it is not just marketing fluff.
The manufacturer is actually signaling that they spent the extra money to physically remove the weak links in the fiber chain. The resulting combed yarn is smoother, finer, significantly stronger, and much less likely to pill than a cheaper carded cotton.
The same principle applies to wool. Carded wool creates scratchy, fuzzy sweaters, while combed wool creates the incredibly sleek, smooth material used in high-end worsted suits.
Now contrast those short staple fibers with filament fibers. A filament is a single continuous strand of practically infinite length. Silk is the only naturally occurring filament fiber. A single silkworm can extrude a continuous thread over 1,000 feet long.
However, all manufactured synthetic fibers, nylon, polyester, acrylic, are born as filaments.
The engineering text describes the synthetic extrusion process, and it sounds bizarrely simple, like a pasta maker.
It really is. The chemical polymers are melted down into a thick, viscous syrup. This liquid plastic is then pumped under high pressure through a device called a spinneret, which looks exactly like a tiny metal showerhead with microscopic holes.
And as the liquid streams exit the holes, they hit the air, or a chemical bath, rapidly cool, and solidify into continuous, solid plastic filaments.
Because these filaments are infinitely long, you do not need to spin them together to create a yarn. Instead, you simply take a bundle of these parallel filaments and give them a very slight twist to hold them together in a process called throwing.
A yarn made of flat, continuous filaments is perfectly uniform. There are no loose fiber ends sticking out anywhere along the shaft. And this structural difference explains a mystery that has always bothered me.
What's that?
Okay, so nylon is used to make rugged, incredibly fuzzy fleece jackets. But the exact same chemical, nylon, is used to make ultra-sheer, perfectly smooth hosiery. How does the same plastic produce two completely opposite textures?
It depends entirely on whether the manufacturer processes the nylon as a filament or a staple yarn. If they want sheer, cool hosiery, they use the extruded multi-filament yarn.
Because the filaments lie perfectly flat and parallel, the resulting fabric is highly lustrous, incredibly smooth, and feels cool against the skin because it makes maximum physical contact to conduct heat away.
It also sheds dirt easily and will never pill because there are no loose ends to tangle into little balls. But flat filament yarns have major drawbacks in clothing.
Right, because they're so dense and smooth, they trap zero air and prevent moisture from escaping, which made early synthetic shirts feel like wearing a clammy plastic bag.
So, if the manufacturer wants to make a soft, warm, fuzzy nylon fleece, they take those infinitely long, extruded nylon filaments and intentionally chop them up into 2-inch pieces, artificially turning them into staple fibers.
That's wild. They cut up the infinite strand just to spin it again.
Yes. They then run those chopped synthetic fibers through the carding and spinning machines exactly as if they were wool.
Because they are spinning short pieces together, the resulting synthetic yarn is covered in millions of microscopic fiber ends poking out from the surface. This creates a fuzzy texture that traps dead air, making the fabric incredibly warm and soft to the touch, though it will now attract lint and is highly prone to pilling.
The industry also developed a hybrid solution, textured filament yarns. They take the continuous, flat synthetic filaments and run them through mechanical gears and heat treatments that permanently crimp, coil, or loop the plastic strands.
So the filaments remain infinitely long, but they no longer lie flat. This texturing introduces bulk and air pockets into the filament yarn, giving synthetics the comfortable, breathable, air-trapping qualities of a spun natural fiber without having to chop into staple lengths.
The final mechanical variable in yarn construction, whether staple or filament, is the twist. When you spin fibers together, the physical tightness of the rotation fundamentally alters the physics of the yarn.
It's like wringing out a towel, right? The mechanics of twist dictate tensile strength. When you apply a soft twist, the fibers are barely held together. The yarn remains bulky, airy, and relatively weak.
But the lack of compression means the yarn is extremely soft and fuzzy, making soft twist yarns essential for weaving warm, brushed fabrics like winter flannels.
If you increase the rotational tension to a hard twist, you force the fibers to compress tightly against one another. The friction between the compacted fibers increases exponentially.
The yarn becomes harder, narrower, and significantly stronger. It resists abrasion better because the fiber ends are locked deep inside the core. Hard twisting also allows engineers to weave incredibly lightweight, sheer fabrics.
By twisting the yarn so tightly, it becomes microscopic in diameter, yet retains enough tensile strength to survive the violent tension of the loom. This is how delicate-looking fabrics like chiffon and voile are structurally possible.
But the textbook details what happens when you push twist to the absolute physical limit, and it's fascinating. You can intentionally over-twist a yarn until it is storing a massive amount of kinetic energy, almost like a rubber band wound too tight.
They use these over-twisted yarns to weave crepe fabric, right?
The kinetic energy release is the defining characteristic of crepe. The loom weaves these extremely highly twisted yarns while they are under tension. But when the finished fabric is washed and exposed to water for the first time, the moisture causes the fibers to swell, and that pent-up kinetic energy violently releases.
The yarns physically kink up, twist back upon themselves, and buckle out of the flat plane of the weave. This microscopic buckling creates the permanent, textured, pebbled surface that we identify as crepe.
So the architecture of the weave and the physics of the yarn twist explain the mechanical behavior of the cloth, but what dictates its chemical behavior?
This leads to the most socially and environmentally loaded topic in our sources: fiber content. Specifically, the ideological war between natural fibers and synthetic fibers.
From a purely chemical standpoint, fiber content is the single most dominant factor determining how a fabric will perform. It overrides the weave and the twist when it comes to fundamental properties like moisture absorption, heat resistance, and chemical resilience.
The textile industry categorizes fibers based on their origin. Natural fibers are grown or raised. We have the cellulosics derived from plants, cotton from seed pods, linen from the stalks of the flax plant, hemp, and jute.
Then we have the proteins derived from animals, wool from sheep, cashmere from goats, and silk extruded by insect larvae.
On the opposing side are the manufactured fibers, synthesized primarily through industrial chemistry. These are derived from petrochemicals, coal, and sometimes natural gas, resulting in polymers like polyester, nylon, acrylic, and spandex.
The debate between natural and synthetic is usually framed as a moral or aesthetic choice, but the textbook zeroes in on a fundamental molecular difference that separates the two camps: their interaction with water.
This is the critical baseline. Natural fibers, cotton, wool, linen, silk are generally hydrophilic. The prefix hydro means water, and ixophilic means loving.
At a molecular level, the chemical structure of natural fibers actively attracts and binds with water molecules. They absorb moisture directly into the core of the fiber, causing the fiber itself to swell.
Conversely, the vast majority of synthetic fibers, polyester, nylon, acrylic, are hydrophobic. They are water-fearing. The plastic polymers do not absorb moisture into their internal structure.
If a polyester fabric gets wet, the water simply sits on the surface of the fibers or fills the microscopic spaces between the yarns, but the fiber itself remains chemically dry and does not swell.
This distinction dictates almost everything about laundry and comfort. Hydrophilic natural fibers take vastly longer to dry because the water is trapped inside the fiber core. They're also highly susceptible to shrinking when agitated in water because of that swelling and contracting action.
Hydrophobic synthetics, because they do not absorb water internally, dry incredibly quickly, resist water-based stains effortlessly, and hold their physical shape exceptionally well during washing.
From an engineering perspective, synthetics sound like superior materials. They don't shrink, they hold a permanent crease because the plastic can be heat set, they are highly resistant to abrasion, and they are immune to the mildew and moths that devour natural fibers.
Yet there is a massive cultural prejudice against them. The sociological analysis in our source material highlights an incredible paradox regarding status.
It is a fascinating application of socioeconomic theory to textiles. Consider the functional reality. A 100% natural cotton or linen shirt will wrinkle the moment you sit down. It will shrink if washed incorrectly. Its dyes will fade rapidly when exposed to ultraviolet sunlight, and eventually the natural fibers will rot and disintegrate.
Meanwhile, a polyester shirt will remain brightly colored, perfectly smooth, and structurally intact for decades without requiring any ironing or special care. It outperforms the natural shirt in almost every measurable metric of durability and ease of use.
Yet society has inverted the value of these properties. The shirt that wrinkles, fades, and requires expensive, tedious care is universally perceived as high status, luxurious, and indicative of good taste.
The synthetic shirt that performs flawlessly is culturally dismissed as cheap, tacky, and low class.
The text explains this through the history of accessibility. When synthetics hit the market, their durability and cheap manufacturing cost made them universally accessible to the working class. Therefore, the wealthy elite, in order to visually distinguish themselves from the masses, embraced the inherent flaws of natural fibers as symbols of exclusivity.
The very fact that a linen suit requires constant, expensive pressing to look presentable became a flex of wealth. A silk drape that rots in the sun is luxurious precisely because it is fragile and expensive to replace, whereas an indestructible, cheap synthetic drape is considered gauche.
We project our socioeconomic anxieties onto the chemistry of the fibers. Furthermore, the rigid moral boundary consumers draw between natural and synthetic is scientifically highly ambiguous.
The categorization is almost entirely semantic. People champion cotton as a pure natural product, but by the time that cotton ball is transformed into a bright blue, wrinkle-resistant dress shirt, it has been subjected to violent mechanical processing, bleached with harsh chemicals, dyed with synthetic chemical compounds, and coated in polyurethane resins to make it behave.
It is a highly engineered industrial product, far removed from nature. We also see the blurriness in the manufactured cellulosics, primarily rayon. Rayon is classified as a manufactured fiber produced in massive industrial chemical plants.
Yet the raw base material used to synthesize rayon is wood pulp. It is pure cellulose, extracted from trees. It is chemically closer to cotton than it is to nylon.
And conversely, the source text points out that the base ingredients for true synthetics, petroleum and coal, are naturally occurring carbon substances extracted from the earth, just like the flax plant. The line between what we consider natural and unnatural is an arbitrary aesthetic preference, not a scientific absolute.
However, there is one area where the distinction between natural agriculture and synthetic petrochemicals does present a massive tangible difference: environmental impact. And as we pivot to the environmental audit data, the common consumer assumptions are violently overturned.
This is where I found myself struggling with the research. Let's play this out. I consider myself an environmentally conscious consumer. I actively avoid buying petroleum-based polyester because it's a plastic that will sit in a landfill for 10,000 years. Instead, I buy pure, natural cotton shirts because they are grown from the earth and are biodegradable. The narrative tells me I am making the ethical, environmentally friendly choice. What does the data actually say about my cotton shirt?
The data dictates that conventional cotton production is one of the most severe environmental disasters on the planet. The agricultural intensity required to yield the sheer volume of cotton the world demands creates staggering amounts of toxicity. The textbook cites a widely accepted, horrifying statistic. Cotton crops consume between 25 to 50% of all the agricultural pesticides used globally.
I thought that was a typo when I read it. Up to half of the world's chemical pesticides are dumped onto a crop we don't even eat.
Yes, cotton is incredibly susceptible to insect devastation, but the chemical load extends far beyond pest control. To prepare the fields, farmers utilize massive quantities of chemical herbicides and synthetic nitrate fertilizers, which rapidly leach into groundwater systems and create toxic runoff in rivers.
And crucially, to facilitate machine harvesting, The cotton plants are heavily sprayed with chemical defoliants, literally poisons designed to kill the leaves so they fall off and don't stay in the white cotton bolls when the machines roll through.
And that's just the farming phase. Once the raw cotton is harvested, the industrial processing begins. The natural fiber is grayish yellow, so it requires enormous volumes of harsh chemical bleaches to turn it white enough to accept commercial dyes.
The dyeing process itself historically creates highly toxic heavy metal sludge that pollutes waterways in manufacturing countries. Finally, to give the cotton consumer-friendly properties like wrinkle resistance, it is soaked in synthetic resins containing formaldehyde, acrylic, or polyurethane.
So your natural, biodegradable cotton shirt is, in reality, a product of severe pesticide application, immense water consumption, and heavy synthetic chemical processing.
What about wool? Sheep are just grazing animals.
The environmental footprint of wool is smaller simply because less of it is produced, but it is not benign. Industrial sheep farming requires millions of acres of cleared land, which leads to habitat destruction and overgrazing that causes soil erosion.
Furthermore, the sheep are regularly submerged in chemical dips containing heavy pesticides like phosphorus or chlorine compounds to prevent parasitic infections. The disposal of these chemical dips is a major agricultural pollutant.
This grim reality provides the synthetic fiber manufacturers with a surprisingly robust environmental defense. Given that polyester and nylon are essentially plastics synthesized from non-renewable fossil fuels, how did the engineers justify their ecological footprint?
The petrochemical industry presents a logically sound counterargument based on resource efficiency and pollution containment. First, they point out that manufacturing synthetic fibers requires absolutely zero agricultural land. Expanding polyester production does not require clearing rainforests or disrupting natural ecosystems the way expanding cotton acreage does.
Second, because there is no agriculture, there is no agricultural runoff. A polyester plant does not dump millions of tons of nitrate fertilizers or toxic insect-killing pesticides into the local watershed.
Third, they address the processing chemicals. Synthetic fibers are extruded from the spinneret naturally stark white. This completely eliminates the need for the massive, water-intensive, highly toxic chemical bleaching processes that cotton requires before it can be dyed.
But the host of solvents and acids used to melt and synthesize the plastics must be incredibly toxic.
They are, but modern synthetic manufacturing frequently utilizes closed-loop chemical systems. In a properly regulated plant, the toxic solvents used to extrude the fiber are not dumped into a river. They are captured, distilled, and continually reused in the next manufacturing cycle.
Furthermore, the synthetic industry has pioneered massive, scalable recycling programs. They are actively consuming millions of discarded plastic water bottles, melting them down, and spinning them into recycled polyester fleece. You cannot easily recycle a blended cotton shirt because the fibers degrade, but plastic can be remelted and re-extruded.
So we have conventional cotton poisoning the earth with pesticides and synthetics relying on finite petroleum extraction. What are the agricultural solutions for natural fibers, and why haven't they taken over the market? The marketing jargon is incredibly dense. I see tags for organic, green, and transitional cotton. What is the actual difference?
The terminology is actively exploited by marketing departments to confuse consumers. Let's define the legal realities. Organic cotton is the strict gold standard. To be legally certified organic, the cotton must be grown entirely without synthetic pesticides or chemical fertilizers, and crucially, it must be grown on land that has been officially certified free of all toxic agricultural chemicals for a specific number of years, usually 3.
Transitional cotton is the stepping stone. A farmer decides to stop using pesticides and switch to organic methods. They are growing the cotton cleanly, but the soil hasn't passed the multi-year waiting period to be certified clean, so they sell it as transitional.
The most deceptive term is green cotton. Green cotton is absolutely not organic. It is conventionally grown cotton, heavily treated with the standard battery of toxic pesticides, defoliants, and synthetic fertilizers.
The green label only applies to the post-harvest manufacturing phase. It simply means the manufacturer used low-impact dyes or skipped the chemical bleaching process. The agricultural devastation was still committed.
Even if a consumer commits to buying strictly certified organic cotton, the data reveals a fatal flaw in relying on it to save the industry: market share. Based on the figures in the audit, out of approximately 13 million acres of total cotton production in the United States, only about 100,000 acres were dedicated to organic and transitional cotton combined.
That is less than 1% of the market. It is a statistical anomaly. Organic cotton is significantly more expensive to farm because it relies on labor-intensive weed control rather than chemical herbicides.
Furthermore, without synthetic fertilizers and pest control, organic crops generally yield significantly less usable fiber per acre than conventional crops. The synthetic industry argues that compensating for this lower yield by clearing more land and using more water to grow organic cotton might actually result in a larger overall carbon and water footprint than producing highly efficient synthetic polyester.
What about completely different natural fibers? Hemp is constantly pitched by environmentalists as the ultimate sustainable textile. It grows incredibly fast, requires practically zero pesticides because it naturally resists insects, and requires far less water than cotton. Why is hemp not replacing cotton globally?
Hemp's failure to dominate the textile market is almost entirely due to legal and political restrictions, not agricultural flaws. In the United States and many other countries, the cultivation of industrial hemp was heavily criminalized or severely restricted for decades. This is because the hemp plant is visually indistinguishable from marijuana, which is an illegal psychoactive drug crop.
Even though the specific strain of hemp grown for textile fibers contains virtually zero THC and cannot be used as a drug, the visual similarity caused law enforcement to ban it outright. This political ban suppressed decades of agricultural and industrial development, preventing hemp from establishing the massive processing infrastructure that cotton enjoys today.
There have also been attempts to environmentally sanitize the manufactured cellulosics. Viscose rayon, while made from renewable wood pulp, historically required an incredibly toxic stew of carbon disulfide and sulfuric acid to break down the wood, devastating the environments around the factories. To solve this, engineers developed lyocell, heavily marketed under the brand name Tencel.
The marketing for lyocell claims it is the perfect sustainable fiber. The wood is supposedly harvested from sustainable eucalyptus farms, and the chemical spinning process is a closed-loop system that recovers 99% of the non-toxic amine oxide solvent. It sounds flawless.
It is a massive environmental improvement over traditional rayon. However, the engineering audits point out a major hidden Achilles heel. The closed-loop spinning process only applies to turning the raw wood pulp into fiber.
The preceding step, the massive industrial process of chopping down trees and chemically cooking the wood chips to extract the raw pulp in the first place, still requires immense amounts of energy and releases significant natural and unnatural chemical byproducts into the environment.
So, if organic cotton is mathematically negligible, synthetics rely on fossil fuels, and green alternatives have hidden pollution costs, how does a consumer navigate the environmental impact of their closet?
The data leads to an uncomfortable, radical conclusion. The environmental crisis is not primarily driven by how the textiles are manufactured. It is driven by the sheer, overwhelming volume of what we consume and discard.
The consumption statistics in the text are staggering. An academic specialist estimated that the annual rate of textile consumption in the United States is approximately 40 kilograms per person. That is almost 90 pounds of new clothing, sheets, and towels purchased by every single individual every single year.
Contrast that with Europe at 20 kilograms, or parts of Asia where consumption is roughly 2 to 3 kilograms per person annually.
That enormous discrepancy highlights the core issue of fast fashion. We treat structurally sound garments as disposable commodities based on fleeting aesthetic trends, but the environmental damage doesn't end at the point of purchase. Comprehensive life cycle analyses of textiles reveal that a garment inflicts its greatest environmental damage after it goes home with the consumer.
The laundering process, the total volume of heated water, the massive energy consumption of electric tumble dryers, and the constant release of chemical detergents and microplastics into the water system over the lifespan of a garment far outweigh the ecological cost of its initial manufacture.
Therefore, the only mathematically and scientifically sound solution to the textile environmental crisis is a radical behavioral shift. The Revolutionary Act is not buying an organic cotton shirt instead of a polyester one.
The Revolutionary Act is ending the cultural hobby of recreational shopping. Consumers must drastically reduce the volume of their purchases, invest in durable, well-constructed fabrics, regardless of whether they are natural or synthetic, wear them significantly longer, learn to mend them, and drastically reduce the frequency of washing and machine drying.
It's a complete rejection of the consumer economy model. But while we're wearing those durable garments for years on end, we have to endure the physical experience of them. This brings us to the actual thermodynamics of dressing and the science of human comfort. How do these complex fabrics interact with the biological machinery of our bodies?
The baseline science of thermal comfort revolves around maintaining equilibrium. Textile scientists note that for a resting human, thermal equilibrium is achieved when the ambient air temperature is approximately 85 degrees Fahrenheit. At 85 degrees, the heat your metabolism generates is perfectly balanced with the heat your body dissipates into the environment. You feel entirely comfortable, completely naked.
If the temperature deviates from 85 degrees, the body reacts. If it drops, blood vessels constrict to preserve core heat, and eventually you shiver to generate friction heat. You feel cold, and you reach for a textile to intervene. We put on a sweater, assuming that the heavy wool is inherently warm and will heat us up.
That is the most persistent misconception in textile science. Fibers do not generate heat, nor are they inherently warm. In fact, compared to materials like metal, all textile fibers, whether wool, cotton, or nylon, are incredibly poor conductors of heat. They are thermally inert.
The mechanism that keeps you warm in a blizzard is not the physical substance of the cloth itself. The insulation is entirely provided by the dead air trapped within the microscopic spaces between the fibers and the yarns.
So when I put on a massive, heavy, fuzzy wool sweater, the wool isn't warming me. My body is radiating heat. That radiant heat warms the layer of air immediately surrounding my skin. The wool sweater is essentially acting as a wearable, three-dimensional architectural lattice designed to trap that layer of body-heated air and hold it stationary. The physical fibers simply serve as a windbreak, preventing the cold ambient air from blowing my personal warm air envelope away.
Precisely. The thermal efficiency of a garment depends entirely on its structural ability to trap air. This is why a highly textured, bulky yarn woven into a thick fabric provides maximum warmth. And crucially, weight does not equal warmth. A garment made of heavily crimped synthetic fleece can be incredibly thick, trapping massive volumes of dead air, yet weigh practically nothing, making it a highly efficient insulator.
Conversely, if the ambient temperature rises above 85 degrees, your body must rapidly shed heat to avoid hyperthermia. It does this by opening blood vessels near the skin and primarily by sweating. The evaporation of liquid sweat into water vapor requires energy, and it pulls that thermal energy directly from your body, creating a cooling effect. The best summer fabrics are designed to facilitate this process.
Summer fabrics must be constructed to hold as little dead air as possible. A thin, tightly twisted linen yarn woven loosely allows ambient breezes to penetrate the fabric and directly strip the heat from the skin.
But dealing with liquid sweat introduces the most critical comfort dynamic, and it completely hinges on that chemical difference we discussed earlier: hydrophilic natural fibers versus hydrophobic synthetic fibers. To understand how dangerous this chemistry can be, we need to examine how these fabrics behave in extreme thermodynamic scenarios.
Let's analyze a high-heat scenario first. Imagine running a marathon on a brutally hot 95-degree summer day. You are wearing a standard hydrophilic 100% cotton t-shirt. Your body sweats profusely to trigger evaporative cooling. Because the cotton is hydrophilic, the fibers actively absorb the sweat, pulling it into the core of the yarn.
The cotton shirt becomes completely saturated and heavy, but in the intense summer heat, that trapped moisture slowly and continuously evaporates off the cotton fibers. As it evaporates, it continuously draws heat energy away from the microclimate next to your skin. The wet cotton acts like a personal swamp cooler. It feels delightfully, refreshingly cool. In a hot weather scenario, the hydrophilic absorbency of cotton is highly advantageous.
Now, transplant that exact same physical mechanism to a cold weather scenario. You are cross-country skiing in 20-degree weather. You are exerting massive physical effort, so beneath your heavy winter coat, your body is sweating heavily. You are wearing that same hydrophilic cotton t-shirt as a base layer.
The cotton absorbs the sweat, becoming saturated just like in the summer.
But the thermodynamic environment has changed. Because the ambient temperature is freezing and the moisture is trapped beneath your coat, the sweat does not evaporate quickly. It stays locked inside the cotton fibers against your skin. When you stop skiing and your heart rate drops, your body stops generating excess heat.
You are now standing in freezing temperatures, wearing a saturated, ice-cold, wet towel clamped directly against your skin.
Exactly. Water is an incredibly efficient conductor of heat, far more efficient than air. The saturated cotton fabric rapidly and aggressively conducts your remaining core body heat away into the freezing environment. Your core temperature plummets. This physical reaction is a direct recipe for rapid, potentially fatal hypothermia. This mechanism is why survival instructors universally preach the mantra, "Cotton kills."
To survive that winter scenario, you must intervene with hydrophobic chemistry. You need a base layer made of a synthetic fiber, like polyester. Because polyester is entirely hydrophobic, the plastic fibers refuse to absorb the liquid sweat. Instead, through capillary action, the fabric physically wicks the liquid moisture away from the surface of your skin, pushing it through the microscopic spaces between the yarns toward the outer layers of your clothing, where it can safely evaporate. Your skin and the synthetic base layer touching it remain physically dry, preserving your body heat.
This wicking capability is the foundation of all modern athletic wear. Early synthetics failed at this because the flat filament yarns packed together so tightly that they trapped the moisture against the skin, feeling clammy. Modern engineering uses textured, crimped synthetic yarns specifically shaped to maximize the capillary channels that physically pump sweat away from the body.
There is one final thermodynamic hurdle that engineers had to solve regarding comfort: water vapor permeability, commonly marketed as breathability. It's not just about letting a breeze in, it is fundamentally about letting evaporated sweat water vapor out.
If a textile is completely impermeable to water vapor, it is unwearable for active use. Consider the physical experience of sitting on a solid vinyl car seat wearing shorts on a hot day. The solid plastic is entirely impermeable. As your skin inevitably transpires, the sweat evaporates into a vapor, but that vapor hits the solid vinyl barrier and cannot pass through.
It has nowhere to go, so the microclimate against your skin reaches 100% humidity instantly. The vapor condenses back into liquid, and you end up sitting in a miserable puddle of your own sweat, feeling incredibly hot and sticky because the evaporative cooling engine of your body has been physically blocked.
Therefore, the holy grail of outdoor textile engineering was creating a fabric that acts as a one-way physical barrier. It must be completely impermeable to liquid water hitting the outside, so the rain cannot soak you, but it must be highly permeable to water vapor on the inside, so your evaporated sweat can escape into the atmosphere.
And the mechanism they developed to solve this is brilliant physics. It's the technology behind Gore-Tex and similar breathable waterproof membranes. They realize there is a massive difference in physical size between a droplet of liquid rainwater and an individual molecule of water vapor.
By taking a synthetic polymer specifically expanded polytetrafluoroethylene and stretching it, they created a microscopic lattice structure filled with billions of tiny pores. The genius of the engineering is the specific size of these pores. They are physically too small for a cohesive droplet of liquid rainwater to penetrate from the outside. The surface tension of the water drop keeps it too large to fit through the hole.
But the pores are hundreds of times larger than a single unbound molecule of water vapor. So when your body sweats and the heat turns it into a vapor gas, those individual molecules easily pass right through the microscopic pores and escape into the air. It selectively filters water based entirely on its physical state of matter. It's an astonishing intersection of physics and chemistry deployed simply to keep a hiker comfortable in the rain.
It demonstrates the incredible depth of science woven into the most mundane aspects of our daily lives.
And that profound depth brings us to the end of our journey through this stack of engineering and historical research. Let's trace the path we've taken. We started by exploring the deep psychological framework of our relationship with cloth, recognizing that our adult aesthetic preferences for soft carpets and heavy drapes are deeply rooted in the infantile search for maternal comfort.
We unraveled the historical labyrinth of modern labels, understanding how the mid-century explosion of synthetic chemistry severed our tactile knowledge of fabrics, forcing us to rely on defensive low-labeling liability tags. We mapped the architectural grid of the textiles, contrasting the interlacing, straight-line stability of plain and twill weaves against the spring-like, interlooping elasticity of knits.
We zoomed in on the mechanical engineering of the jacquard loom, realizing that the punch cards used to weave decorative upholstery were the binary blueprints for the entire digital age. We deconstructed the yarns, learning how combing physically removes weak fibers, how twist manipulates tensile strength and kinetic energy, and how the difference between chopping a staple fiber and extruding a continuous filament dictates whether a nylon jacket feels like a fuzzy fleece or a smooth plastic.
We examined the socio-economic status games that compel us to view the functional flaws of natural fibers as luxurious and the durability of synthetics as cheap. We confronted the grim environmental audits, exposing the myth of pure cotton by detailing its massive pesticide load and chemical processing, while acknowledging the fossil fuel realities of the closed-loop synthetic industry.
And we broke down the relentless physics of thermal comfort, proving that garments don't warm us, they merely trap our own dead air. We explored how the hydrophilic nature of cotton can cool us in the summer or induce hypothermia in the winter, and how microscopic pores manipulate the physical state of water to keep us dry. It is an overwhelming amount of hard science and history hidden in plain sight.
I want to leave you with a final thought to mull over, one that expands on everything we've analyzed today. The next time you get dressed, before you throw on a shirt or pull up a blanket, take a moment to look closely at the physical material. Look past the color, past the brand name, and past the printed care label. Ask yourself, what invisible architecture are you utilizing to mediate your relationship with the physical world today? Are you wrapping yourself in a hydrophobic, heavily engineered synthetic shield, extruded from ancient petroleum and optimized for thermal capillary action? Or are you wearing a hydrophilic, tightly twisted plant fiber that carries the heavy water footprint, the chemical history, and the deep agricultural legacy of the soil it was grown in?
Your clothing is not just a passive fashion statement or a simple barrier against the wind. It is an active, profoundly complex intersection of structural engineering, molecular chemistry, global agriculture, and deep human psychology, operating continuously 24 hours a day right against your skin. Thank you for joining us on this deep dive. Picture the absolute lengths human beings will go to, just to avoid doing a chore.
Oh, people will do anything.
Literally anything. So picture this. It's the late 17th century. You're an aristocrat living in France.
Okay, setting the scene.
Right. And over the past month, your household has accumulated just this massive pile of soiled linens, undergarments, fine lace, all of it.
A literal mountain of laundry.
Exactly. But you don't hand this over to the local staff to take down to the river. And you definitely don't, boil water in your courtyard.
No, that would be far too practical.
Right. Instead, you pack these incredibly heavy, dirt-caked linens into wooden crates. You load those crates onto a massive galleon, and you ship them across the Atlantic Ocean to the Caribbean.
I mean, it sounds like an exaggeration, right? But it was a documented logistical reality for a very specific subset of the ultra-wealthy.
It's just wild to me. Months at sea.
Yeah, they were willing to subject their clothing to months at sea, the corrosive nature of salt air, and, frankly, immense financial cost.
Just to avoid laundry?
Exactly. Just to utilize the natural resources and the labor available in the colonies rather than deal with the overwhelming physical burden of laundering at home. I mean, the sheer desperation to offshore the physical labor is a testament to how grueling the process was back then.
It really is. And, we look at the laundry hamper today with a certain level of existential dread, sure, but we certainly aren't chartering transatlantic voyages to empty the thing.
No, thankfully.
We just toss a few shirts into a metal box, pour a cup of some random neon blue liquid over them, hit a button, and walk away.
Right, but that convenience has actually created this modern sort of casino.
A casino, I like that.
Yeah, because we pull the lever on the machine and just blindly hope that our favorite sweater doesn't emerge from the spin cycle looking like it was sized for a toddler.
Or tinted some bizarre, sickly gray color. I have absolutely done that.
We all have. And the irony here is that the automation of the chore removed our mechanical understanding of it.
What do you mean by that?
Well, when laundry required boiling vats, wooden wringers, and heavy scrubbing boards, the person doing the wash had this really intimate, tactile understanding of what the fabric could endure.
You could literally feel if you were destroying the shirt.
Exactly. But today, the machine handles the brute force, which means that effectively cleaning your clothes now is no longer a physical challenge. It's evolved into a purely intellectual exercise.
So it's not about muscle anymore.
No, it's a calculated application of physics, chemistry, and material science.
And that right there is the core mission of our deep dive today.
Yeah.
We're taking a really comprehensive stack of source materials. We've got historical household management texts, modern textile science manuals, chemical engineering guides.
Some really dense reading.
Very dense. But we are distilling the exact mechanics of clothing care for you. The goal is to shortcut all that trial and error.
So you can stop prematurely aging your wardrobe.
All right. By the time we finish this, you are going to understand the invisible forces at work inside that metal drum. We want to help you transform that chaotic, fabric-ruining gamble into an efficient, highly controlled routine.
But to truly control that routine, we have to understand why we're even doing this in our private homes in the first place.
It wasn't always the norm, right?
Not at all. The historical pendulum has swung wildly. If we look back to, say, the year 1900, the urban custom was largely to send laundry out.
Right.
Commercial laundries were ubiquitous in cities, and the reason was entirely practical.
Because doing it at home was impossible.
Basically, doing laundry at that time required immense infrastructure. You needed dedicated boilers. You needed industrial mangles.
Thanks, it's mangle.
Oh, they were these massive, incredibly dangerous heated rollers used for pressing flat linens.
Sounds terrifying.
It was. Plus, you needed heavy seat irons and just significant square footage just to dry all those textiles. A standard city apartment simply couldn't support the equipment or the sheer muscle power required.
I mean, that makes complete logistical sense. If cleaning a shirt required me to fire up a coal boiler in my kitchen, I would be handing my laundry to a professional service tomorrow, without hesitation.
Exactly. But then, the advent of the automated washing machine changed the urban landscape almost overnight.
So everyone bought a machine, and the commercial places died out.
Pretty much. Commercial laundries began vanishing by the hundreds as the private home reabsorbed the sole responsibility for the job.
Wow.
And our historical sources highlight a really fascinating sociological reaction to this. There were feminist writers and activists at the time who bitterly complained about the invention of the home washing machine.
Wait, really? They complained about it.
Yes, they had viewed the industrialization of laundry, its removal from the domestic sphere into commercial enterprises, as this definitive victory in freeing women from relentless housekeeping.
Oh, I see. So bringing it back into the house.
Was perceived by some as that hard-won battle being lost. The automated machine bringing the chore back inside was seen as a step backward.
That is fascinating. I had never considered the appliance as a step backward for household labor just because of its location. Like, it democratized the chore, sure,
Yeah.
but it also anchored it right back in the living room.
Exactly. And that historical shift naturally prompts a question for the modern listener, right?
Yeah, like, if you're a stressed, dual-income household today, overwhelmed by chores, why not just revert to that 1900s model?
Why fight this battle at home at all?
Right. Why not just use a modern wash and fold service and be done with it?
Well, the sources break down the factual trade-offs, and they center entirely on the physics of textile degradation.
So it's about ruining the clothes.
Yes. Setting aside the significant financial cost, commercial laundering fundamentally cannot provide individual, customized attention to specific garments.
Because they have to move fast.
Right. Commercial facilities optimize for speed and volume. And to get speed and volume, you have to rely on heavy-duty industrial detergents, high heat, and intense mechanical agitation.
So they're just blasting the clothes.
Essentially. The reality is that commercial laundering accelerates the wearing and fading of fibers at a staggering rate. You are trading convenience for the lifespan of the garment.
That makes sense.
To maintain the structural integrity and those vibrant dyes of your wardrobe, you have to be the one controlling the chemistry.
So it's a stark choice. You either possess high-quality items that last, or you accept that your clothes are essentially disposable because someone else is subjecting them to an industrial meat grinder.
That's a great way to put it.
So if we are taking control, we need to look at how often we are firing up this machine. The sources talk about this historical concept of Blue Monday. What is that?
So in the 19th century, Monday was the designated day for this grueling work. Sunday was the day of rest, obviously.
Okay.
And the sheer physical exhaustion required for laundry meant it had to be tackled on Monday before the household's energy was spent for the week.
So you just get it out of the way.
Yeah, but it was such a miserable, steam-filled, back-breaking day that it literally depressed the entire household, hence the name Blue Monday.
Wow. We've really gone from dreading a massive weekly production to a culture of just, like, hyper-convenience.
Oh, absolutely.
I know people who will throw a single pair of jeans and a T-shirt into the machine on a Wednesday evening simply because they want to wear them to dinner on Thursday. We use the washer like a magic closet
Which is scientifically counterproductive.
because of the wear and tear.
Yes. The mechanical analysis in our source material is definitive here. Washing your clothes once or twice a week is vastly superior to daily ad hoc laundering.
Let's examine the mechanics of that. Why is frequent washing actually detrimental? I mean, besides the obvious water waste.
It comes down to fluid dynamics and load balancing. Daily laundry inherently means washing very small loads, right?
Right.
Well, a washing machine is engineered to clean via the friction of items moving against one another in an aqueous suspension.
So the clothes need to rub together.
Exactly. If the load is too small, that crucial fabric-on-fabric abrasion just doesn't happen efficiently. And furthermore, a small load cannot balance the centrifugal force of the spin cycle.
Oh, that's why the machine gets unstable.
Right. That's when you hear that terrifying banging sound as the drum literally dances across the floor.
I hate that sound.
Accumulating a substantial stock of laundry ensures medium to large loads. In a larger load, items of varying sizes mix loosely, allowing the water and detergent to flow freely while maintaining the mechanical balance of the machine.
So we are over-laundering merely because the appliance is constantly available to us. But putting cloth through water and agitation isn't a neutral event, it's a destructive one.
Highly destructive.
It reminds me of caring for, like, a carbon steel wok or a cast iron skillet.
Oh, that's a perfect analogy.
Right. You don't take a highly abrasive steel wool pad and scrub a cast iron pan with heavy soap after every single use. You wipe it out, you maintain its seasoning, you respect the material.
Yes.
Yet, with a shirt, we might wear it for 3 hours, sitting quietly in an air-conditioned office, and we instantly toss it into the hamper to be subjected to chemical detergents and mechanical beating.
It's so true. We really need to reframe how we view the soil on our clothes. We tend to conceptualize dirt as merely an aesthetic issue, like a smudge or a coffee stain.
Right, if I see it, it's dirty.
But on a microscopic level, particles of dust and dirt act as abrasive weapons.
Weapons.
Yeah, dust is primarily composed of silica, quartz, and other incredibly hard minerals. When these microscopic particles embed themselves into the weave of a cotton or wool fabric, they act like tiny saws.
So it's not just sitting on the surface. As I walk around, the movement of my body is grinding those silica particles into the threads.
Yes. The friction of your movement causes those sharp, hard minerals to physically cut into the softer cellulose or protein fibers of the cloth.
Oh, wow.
It weakens the structural integrity of the garment and makes it highly susceptible to spontaneous holes and tears.
So you have to wash it to get the tiny saws out.
Exactly. You are forced to wash the garment to extract the microscopic knives. But that, as we established, the mechanical agitation of the washing machine also degrades the fiber.
It's a lose-lose situation.
It really is a delicate, continuous negotiation between removing the abrasive dirt and minimizing the damage inflicted by the machine itself.
So the ultimate goal, then, is to reduce the volume of items entering that negotiation in the first place.
Yeah.
Without, resorting to wearing unsanitary clothes.
Right. And the source texts outline a really robust system of preventative maintenance to drastically reduce weekly laundry volume.
Give me some examples.
So bath towels, for instance. They should be hung meticulously over a wide bar after use, not just bunched up on a hook.
Because of mildew.
Yes. It allows air circulation to evaporate the moisture before mildew spores can colonize the damp terry cloth.
What about clothes?
Outer garments like sweaters or trousers that are worn lightly should be spot cleaned with the damp cloth and allowed to air out on a hanger overnight.
So they release the smells.
Right, to release absorbed odors rather than being banished immediately to the dark, airless hamper.
That makes sense.
And wearing a lightweight, washable base layer, like a t-shirt, camisole, or slip, creates a sacrificial barrier. It absorbs perspiration and body oils, protecting the more complex, difficult-to-wash outer layers.
Okay, so we've minimized the volume through maintenance. We've aired the wool, hung the towels, we've got our base layers on. But inevitably, the hamper does fill up.
It always does.
And we are faced with this chaotic mountain of textiles. Which brings us to what the sources identify as the absolute core of this intellectual exercise.
Yeah.
The physical sorting.
Yes. The initial sorting of the hamper represents a really fascinating modern crisis.
I love how the texts touch on this cultural attitude they describe as youth nihilism toward laundry.
It's a very real phenomenon.
It's this pervasive belief that the rules of sorting are just these archaic fictions. You see people scooping up a heavy dyed denim jacket, a fragile white synthetic blouse, and a bright red towel, tossing them all into the drum simultaneously, completely convinced that modern machines have somehow rendered sorting obsolete.
And that nihilism is a direct reaction to modern complexity. Consider the benchmark from 1861.
Mrs. Beeton's book.
Yes, Mrs. Beeton's highly influential book of household management. Her sorting directives were incredibly strict, but fundamentally simple because the material world was simple.
How many categories did she have?
The manager of the house separated white linens into one pile, fine sheer muslins into a second, colored cottons into a third, woolens into a fourth, and heavy, greasy kitchen cloths into a fifth. 5 distinct, easily identifiable categories.
That sounds lovely. But today, the textile landscape is an absolute minefield.
Oh, it's a nightmare.
We are dealing with elastane, modal, bamboo rayon, polyester blends, specialized chemical finishes for water resistance, and deeply contradictory care labels.
Yes. The author of one source notes inspecting a single medium-sized load of casual clothing and discovering 10 completely distinct sets of laundering instructions stitched into the collars.
10.
10. If a person actually obeyed every esoteric symbol on those tags, they would be running 30 microscopic, highly specific loads of laundry every week.
So the sheer impossibility of following every label breeds the nihilism you mentioned. People just abandon the attempt entirely.
Exactly. But the cost of that abandonment is insidious.
Insidious how?
Because it's rarely a catastrophic immediate failure. You don't often pull a shirt out and find it completely shredded on the first wash. The damage is cumulative.
So it creeps up on you.
Yes. Over several months of unsorted washing, unstable dyes sublimate in the water. That turns an entire wardrobe of light colors into a dull, uniform, muddy pink or dingy gray.
Oh, I've seen that gray color.
And the mechanical friction of heavy denims against soft knits causes severe pilling. That's where broken fibers knot into little spheres on the surface.
Which makes a sweater look 10 years old after 3 washes.
Exactly. People assume that maintaining a crisp, vibrant wardrobe is a luxury reserved for the wealthy, when in reality they are systematically destroying the optical brightness and structural integrity of their own investments simply by skipping the sort.
So we need a functional architecture to cut through the noise of those 10 different care labels. We obviously can't do 30 loads, but we can't do 1. What is the overarching framework?
The literature synthesizes this into 5 non-negotiable rules for sorting.
Okay, let's go through them.
Rule 1 is sorting by washing method. This determines the level of mechanical agitation a fabric can physically withstand, categorized generally as regular, permanent press, gentle, or hand washing.
And what's the principle for mixed items?
The crucial principle here concerns blended or multi-fabric garments.
I assume it's a lowest common denominator situation. Like if I have a heavy cotton dress that features a delicate sheer chiffon collar, the sturdiness of the cotton is totally irrelevant. I am holding the entire garment hostage to its most fragile thread.
A perfect articulation. You must always default to the cycle required by the most delicate component, otherwise the cotton dress survives, but the chiffon collar just disintegrates.
Makes sense. Was it rule 2?
Rule 2 addresses color, and the texts are absolutely militant regarding the definition of white. Militant. White is an absolute. Off-white, cream, ivory, or white fabric with a minuscule pastel print do not qualify. Pure whites must be isolated.
Okay, pure whites only.
The rest are categorized into lights, mediums, and darks, keeping similar hues like deep blues and purples together.
Let's interrogate that strict definition of white for a second. If I have a pale cream shirt, what is the actual chemical or optical harm in washing it with a pure white t-shirt? It's basically the same color.
The danger lies in the physical properties of modern synthetic whites, particularly nylon and polyester. These fibers are highly porous at a microscopic level.
So they act like sponges.
Exactly.
Yeah.
They act as absolute sponges for stray dyes suspended in the wash water. Even an invisible microscopic amount of pastel dye bleeding from a cream-colored shirt into the warm water will be readily absorbed by a white nylon undergarment.
Wow, even if I can't see the dye in the water.
Even then, it alters the optical refraction of the synthetic fiber, turning it permanently cloudy or gray. And once that dye bonds to the synthetic matrix, it is nearly impossible to extract.
That explains so many ruined t-shirts. Okay, so rule 3.
Rule 3 focuses on soil level. The objective is keeping heavily soiled items, muddy trousers, mechanics overalls, entirely segregated from lightly worn items.
Why? Won't the detergent just clean everything?
The risk here is the phenomenon of redeposition.
Redeposition. What's that?
So the surfactants in the detergent lift the heavy grease and soil from the muddy trousers, suspending it in the water. But if you have included a lightly soiled white t-shirt in that same water, the sheer volume of suspended dirt overwhelms the chemical capacity of the detergent to hold it.
Oh, no.
Yes. The dirt physically detaches from the water molecules and redeposits itself evenly across the surface area of the white t-shirt. The t-shirt effectively acts as a physical filter for the contaminated water.
My t-shirt becomes a water purifier for my jeans.
Unfortunately, yes.
That is a visceral warning.
And there's an addendum to soil level highlighted repeatedly in historical and modern texts. Items containing biological waste, specifically cloth diapers, must be washed in complete isolation to prevent massive bacterial cross-contamination.
Absolutely zero compromises on diapers. Got it. What's rule 4?
Rule 4 requires sorting by mechanical damage. This is separating the aggressors from the vulnerable.
The fighters and the victims.
Exactly.
So a pair of heavy cargo pants laden with brass zippers, metal rivets, and thick Velcro straps cannot be allowed in the same drum as an open weave lace top. The zippers will act like teeth, snagging and tearing the open weave during the spin cycle.
Precisely. But mechanical damage also encompasses the physics of static electricity and friction, specifically regarding lint. You must isolate lint producers from lint attractors.
Break down the mechanics of lint attraction for me. Why does one fabric shed while another collects?
It involves the structure of the yarn and the triboelectric effect.
The what?
The triboelectric effect, it's static electricity. A new plush terry cloth towel or a loosely woven flannel shirt is constructed with short, loosely spun fibers designed to feel soft. The mechanical agitation of the wash easily snaps these short fibers, releasing them into the water as lint.
Okay, so those are the producers.
Right. Conversely, fabrics like corduroy have a textured pile that physically traps debris, and synthetic fabrics like polyester generate strong static electric charges when rubbing against other materials.
So they pull the lint to them.
Yes. If you wash the shedding terry cloth with the static charged polyester, the polyester acts as an electromagnet, permanently pulling the loose cotton fibers into its weave.
I have spent hours with adhesive rollers trying to undo that exact mistake.
It's the worst.
So we have washing method, color, soil level, and mechanical damage. But if we stringently apply all four of those, we are right back to 30 tiny loads.
Which brings us to the fifth and most critical rule: compromises.
Okay, finally. How do we compromise safely?
The intellectual art of laundry is knowing how to bend the first four rules safely to combine loads for efficiency. For example, consider a load of white synthetic garments and a load of white natural fiber garments.
Okay, two different materials, both white.
The natural cottons can withstand a harsh, regular wash cycle. The synthetics require a gentler, permanent press cycle to avoid heat damage. The compromise is combining them into a single load and running the permanent press cycle.
So you default to the gentler cycle.
Right. The cottons might not receive their maximum tolerated agitation, but they will still clean effectively, and the synthetics remain protected.
Compromising on cycle strength makes total sense. But compromising on color seems like playing Russian roulette. Like if I have a brightly patterned shirt and I suspect the dye might be unstable, I don't want to risk the rest of the load, but I also refuse to wash a single shirt in 40 gallons of water.
This is where chemical testing replaces guessing. The source material shares a really cautionary anecdote regarding a brightly colored child's bathing suit.
What happened?
The manufacturer's care label explicitly stated machine washable. However, the very first time the child waded into ordinary cold lake water, the red stripes violently released their dye, staining everything nearby.
So the dye bonds failed in unheated lake water, completely contradicting the printed label.
Exactly. It proves that care labels are not infallible legal contracts, they are guidelines. To protect your load, you must test for color fastness before committing a suspicious garment to the machine.
How do you do that without ruining it?
The sources detail a highly effective 10-minute chemical test. You take 1 teaspoon of the exact detergent you intend to use and dissolve it in a cup of water heated to the exact temperature of your planned wash cycle.
Okay.
You locate a hidden seam allowance or an inside hem of the garment, dip it into the concentrated solution, wait a few minutes to allow the chemical reaction to occur, and then press a clean white paper towel firmly against the wet fabric.
And if it bleeds?
If even a microscopic tint of color transfers to the paper towel, the dye bonds are unstable. The garment is a bleeder and must be isolated.
That is brilliant. A simple spot test that prevents the catastrophic ruin of an entire wardrobe.
It takes 10 minutes.
So we have successfully negotiated the hamper. We have our strategic, scientifically compromised piles. The subsequent phase is the pre-game inspection, the physical preparation of the garments before they encounter the water.
This stage addresses the concentrated physics of daily wear. The first line of defense is targeted pre-treating.
I have to admit, pre-treating often feels like a hopeful spray in the dark for me. I find a stain, saturate it, and cross my fingers. But there must be specific friction zones we should be preemptively attacking.
Absolutely. You are looking for the areas of the garment that endure the highest localized friction against human skin. Collars and cuffs are the primary targets because they act as abrasive sponges for sebum, the natural oils secreted by the body.
Sure, collar around the neck. That makes sense.
But the texts point out a highly overlooked zone, the undersides of the forearms and the stomach area.
With the stomach area, what is the mechanism of action there? Why is my stomach getting dirty?
Think about your posture at a desk or a dining table. You are constantly resting your forearms and leaning your abdomen against hard surfaces.
Oh, you're right.
And those desks harbor microscopic layers of dust, graphite, ink, and ambient room oils. Your body weight actively grinds that ambient dirt deeply into the fibers of the shirt.
That is kind of gross to think about.
By pre-treating these specific friction zones with a concentrated liquid detergent or an enzymatic spray before the wash, you give the chemistry a head start. The concentrated surfactants begin breaking the lipid bonds of the body oils before the water ever touches the fabric.
Okay, here is a persistent debate regarding preparation, turning clothes inside out. Some manuals swear it is the ultimate preservation technique, others totally dismiss it. What is the actual mechanical rule?
It is a deliberate compromise between surface protection and soil removal.
Okay, explain.
The mechanical reality is that turning a garment inside out forces the interior surface to take the brunt of the agitator's physical beating. This is absolutely essential for dark denims, corduroys, and synthetic knits that are highly prone to surface pilling and dye abrasion.
So you preserve the exterior aesthetic by sacrificing the interior.
Exactly.
But logically, if I spill a cup of coffee down the front of my shirt, or if a child slides in the mud, the heavy soil is concentrated on the exterior. By turning it inside out, am I not folding the dirt inward, creating a physical barrier that the water and detergent must fight through?
You are precisely identifying the trade-off. Yes, turning it inside out makes heavy exterior soil more difficult to extract. The water pressure must force the dirt through the weave from the inside out.
So what do we do?
It requires a risk assessment. If a pair of jeans is lightly worn and you want to preserve the dark indigo dye, turn them inside out. If those same jeans are caked in heavy garden mud, you must leave them right side out to allow direct chemical and mechanical access to the soil, accepting a minor degree of dye abrasion as the cost of getting them clean.
It is a constant negotiation.
Yeah.
All right, I want to address a phenomenon that borders on household mythology.
Oh, I know where this is going.
The washing machine consuming socks. Is there an actual physical void within the plumbing where small textiles disappear?
It is a very pervasive myth, but the engineering of the machine debunks it entirely. A washing machine does not eat socks.
Walk me through the plumbing then. Why is it physically impossible?
Well, the water exit valve at the base of the machine's drum leads to a drain pump, and that pump is protected by a rigid filter or a highly restrictive grate. A textile item the size of a sock physically cannot pass through that grate into the drainage plumbing without instantly jamming the impeller and halting the machine entirely.
So it can't escape down the pipe.
No. When a small item seems to vanish, it has not left the sealed system of the drum.
And where on earth do they go?
They are hidden by the immense hydraulic pressure of the wash cycle.
What do you mean?
The force of the water and the twisting of the agitator forces small, pliable items into the sleeves of heavy shirts, deep up into the legs of trousers, or, most commonly, they are pressed completely flat and folded into the elasticized corners of fitted bed sheets.
Oh, so they're just hiding.
They are hiding in plain sight, camouflaged by the mass of wet fabric. The engineering solution to this physics problem is incredibly simple. Utilize a zippered mesh laundry bag.
Because it keeps them contained.
Right. Confining all hosiery and small items in a porous bag ensures the water flows through, but the items cannot be dispersed by the hydraulic pressure.
A $2 mesh bag defeats the greatest mystery of the laundry room. I love it. Speaking of hidden items, leaving objects in pockets is a universal failure. A forgotten tissue turning into a blizzard of white flakes is annoying, but the sources indicate that hard objects present a severe mechanical danger.
A tissue requires a lint roller. A forgotten coin or a metal key requires a technician.
A technician, why?
When dense, metallic objects are left loose in the drum, the extreme centrifugal force of the spin cycle turns them into projectiles. They are hurled against the interior wall of the washing tub. Most standard tubs are constructed of steel coated with a smooth, baked enamel finish to protect the clothes.
So a flying quarter strikes the wall and chips the enamel.
Exactly. The impact fractures the smooth enamel, exposing the raw steel underneath. That exposed steel quickly develops a microscopic layer of rust, creating a jagged, rough burr on the wall of the drum.
Oh, that sounds bad.
You have effectively installed a cheese grater inside your washing machine. For years afterward, every time a delicate silk or a fine knit brushes against that invisible rough patch during a high-speed spin, the fibers will catch and snag.
That's horrifying.
One forgotten key can systematically destroy garments for a decade.
Check your pockets. Always. Okay, so we have meticulously sorted, pre-treated, inverted the denims, and cleared the pockets. We finally lift the lid of the machine. But what exactly is the machine doing? To the casual observer, it just looks like a chaotic, sloshing vat of water.
The internal mechanics are probably the most fundamentally misunderstood aspect of the chore. Consider the three standard cycles on a traditional top-loading machine: regular, permanent press, and gentle.
Yeah, the three main buttons.
Right. These are not merely suggestions for soil levels, they are distinct, highly engineered mechanical choreographies.
The regular cycle always appears deeply violent to me.
Mm.
It looks less like cleaning and more like a mosh pit.
The mosh pit is a highly accurate mechanical metaphor.
Really?
Yes, the regular cycle utilizes rapid, vigorous agitation. The central post, which is equipped with spiraled vanes, aggressively jerks and pulls the fabric mass back and forth through the water. It uses kinetic energy to force the water molecules rapidly through the microscopic spaces between the woven threads,
So it's basically blasting the dirt out.
literally blasting the dirt particles out of the matrix. This reveals the central paradox of all laundering. The physical abrasion required to remove the dirt is the exact same physical force that eventually destroys the garment.
The violence is necessary to blast silica out of heavy cotton canvas, but that same kinetic energy will physically tear the delicate protein fibers of a silk blouse to shreds.
Which necessitates the gentle or delicate cycle.
How does that one work?
It slows the oscillation of the agitator to a lazy sway, drastically reducing the kinetic energy and the resulting abrasion. It protects structurally weak fibers like rayon, which, by the way, loses up to half its tensile strength when wet from being ripped apart by the hydraulic shear forces.
So the regular cycle is brute force, the gentle cycle is preservation. But what is happening during the permanent press cycle? It feels like the ambiguous middle child. I always assumed it was just a marketing buzzword for, like, office shirts.
Oh, not at all. Permanent press is a thermodynamic marvel designed specifically to address the physical properties of modern synthetic fibers like polyester, nylon, and treated wrinkle-resistant cottons.
Okay, thermodynamics, tell me more.
Synthetics are, at a molecular level, extruded plastics. They are thermoplastic, meaning their structural rigidity is entirely dependent on temperature.
So if I wash a polyester shirt in warm water, the heat causes those plastic molecules to relax. The fiber becomes pliable like a warm piece of wax.
Exactly. Now, consider a traditional regular cycle. It transitions immediately from a warm wash to a high-speed spin cycle while those plastic fibers are still warm and pliable.
Oh, I see where this is going.
The extreme centrifugal force smashes the pliable garment against the wall of the drum, folding it into sharp creases. As the water drains and the garment cools in that crushed state, the plastic molecules lock back into a rigid structure.
You are literally baking the wrinkles into the molecular structure of the shirt.
Yes, you can iron it for an hour and those creases will never fully release.
So how does the permanent press cycle alter that thermodynamic process?
It employs the aggressive agitation of the regular cycle to achieve soil removal. But before the spin cycle begins, it introduces a crucial step: an automatic, slow, cold water rinse.
The cool down phase.
Yes, this cold water shocks the warm, pliable synthetic fibers, instantly dropping their temperature and freezing them back into a rigid, smooth state while they are still floating freely in the water.
It sets the molecular structure while the shirt is relaxed, so when the extreme force of the spin cycle hits, the fibers are already locked in a smooth configuration and resist creasing. That is brilliant engineering.
It really is a perfect synchronization of chemistry and mechanics. Now, those dynamics apply to the traditional American top-loading machine with a central agitator. But there is a massive shift toward horizontal axis, front-loading machines, heavily influenced by European designs.
The expensive machines with the glass doors on the front, are the mechanics inside genuinely superior? Or is it just an aesthetic status symbol?
The physics are fundamentally different, and the data regarding efficiency is staggering.
How so?
Well, a traditional top loader cleans via suspension. It floats the clothes in a massive vat of roughly 30 to 40 gallons of water and beats them with a plastic stick.
Right.
A front-loading horizontal axis machine relies entirely on gravity. It rotates the drum, lifting the wet clothes to the top of the arc, and allows gravity to drop them into a very shallow pool of water at the bottom.
Oh, so they just fall.
The impact of the clothes hitting the water provides the necessary kinetic energy to blast out the dirt. Because it doesn't need to suspend the clothes, a European-style front loader uses only 15 to 17 gallons of water.
It cuts water consumption by more than half simply by weaponizing gravity.
Furthermore, they consume roughly 65% less electrical energy. And because the horizontal drum can spin at exponentially higher revolutions per minute without becoming unbalanced, the centrifugal force extracts far more water, leaving the clothes nearly dry to the touch and massively reducing the time and energy required in the dryer.
If the physics are that superior, what is the drawback? Why hasn't the suspension model gone completely extinct?
The trade-offs are time and temperature. Because front loaders utilize a fraction of the water, the gravitational impact process takes significantly longer to achieve the same level of soil extraction.
How long are we talking?
A standard wash cycle on a European machine can take an hour and a half to 2 hours.
Wow, that is a long time.
Additionally, many of these advanced front loaders bypass the household water heater entirely. They connect only to the cold water line and utilize internal high-efficiency heating elements to bring the small volume of water to highly precise temperatures.
Having the machine control its own water temperature sounds incredibly efficient, though.
It is until you realize that some of these machines, designed for heavy European linens, can heat the internal water pool to temperatures exceeding 200 degrees Fahrenheit.
200 degrees is essentially boiling water.
It is phenomenal for thermally sanitizing white cottons and heavy canvas, but if you unknowingly subject a modern, dye-sensitive synthetic athletic shirt to a 200-degree bath, the thermoplastic fibers will literally melt, and the dyes will instantly flash off into the water.
That would be a disaster.
The operator must be highly vigilant regarding the machine's internal thermostat.
Which brings up a critical mechanical failure point regardless of the machine's orientation. The danger of overcrowding.
Yeah.
We are all guilty of it. The hamper is empty, but there is one heavy bath towel left on the floor. You use your foot to physically shove that towel into the drum just to get it out of the room.
The desire for total completion is understandable, but overcrowding fundamentally breaks the physics of the machine, particularly for synthetic and knit fabrics.
Why is it so bad?
These materials require significantly more water volume and less physical crowding than sturdy cottons. A washing machine cleans by forcing water through the textile. If the drum is packed solid, the items cannot move independently.
So the gravitational drop in a front loader doesn't happen, and the agitator in a top loader just twists the entire solid mass of laundry back and forth as a single block.
Precisely. The required fabric-on-fabric abrasion drops to zero. The doot cannot detach, the detergent cannot penetrate the center of the mass, and the garments emerge trapped in a severe tangled knot.
So they don't even get clean.
No, and the resulting friction damage and deeply set wrinkles are catastrophic. The mechanical rule is that a load of permanent press or knits should never exceed a medium fill, and the water level must always be set one size larger than the physical volume of the clothes.
So you have to give the clothes room to swim.
Exactly.
Okay? The machine provides the mechanical muscle. It spins, it drops, it agitates. But the invisible magic and the arena with the highest potential for total ruin is the chemistry of the water. Let's delve into temperature.
Temperature is the master switch that controls the entire chemical process. Yet human perception of water temperature is deeply subjective and heavily influenced by geography.
We discussed this earlier. Like, if I turn on the cold tap in Florida in the middle of August, the water coming out of the pipes has been sitting in sun-baked ground. It feels like a tepid bath.
Right.
But if a friend turns on the cold tap in Michigan in January, the water is hovering just above freezing. It hurts your hands.
And that geographical discrepancy is critical because chemical detergents are entirely beholden to thermal energy. The textile science is unanimous. Modern laundry detergents effectively cease to function in water that drops below 65 degrees Fahrenheit.
The chemicals just go dormant. How does that work on a molecular level?
Detergents rely on surfactants molecules with a hydrophilic head that loves water and a lipophilic tail that loves oil. They act like microscopic crowbars, prying the body oils off the fabric and suspending them in the water.
Okay.
But those molecules require a minimum amount of thermal energy to move fast enough to do their job. Below 65 degrees, the activation energy is simply too low. The surfactants become sluggish.
So they just stop working.
Furthermore, powdered granular detergents rely on heat to dissolve. In 40-degree winter water, the powder simply clumps into hard, soapy rocks.
So if I wash a load of dark shirts in frigid Michigan tap water, the detergent isn't pulling the oil out of the collars, and I'm likely to pull the shirts out covered in undissolved white powdery streaks. But every ecological campaign urges consumers to wash in cold, to conserve energy and save the planet.
The ecological advice is sound, but the consumer must understand what the machine's definition of cold actually is.
What does the machine think cold is?
The Federal Trade Commission established standardized definitions for washing machine manufacturers. Hot water is defined as 130 degrees Fahrenheit or higher. Warm is a mixture ranging from 90 to 110 degrees. Cold is defined as 80 degrees or below.
Okay, so cold is under 80.
But And this is the critical caveat that ruins wardrobes. It must not drop below that 65-degree chemical baseline.
Ah, so if my tap water is 40 degrees in the winter, setting the dial to cold means I am washing in chemically inert water.
Right.
I actually have to set the dial to warm just to inject enough hot water to raise the temperature to 65 degrees, hitting the chemical definition of cold.
It requires managing the localized variables of your own plumbing. The experts actually advise taking a basic cooking thermometer and physically measuring the temperature of the water flowing into the drum.
Really? A cooking thermometer?
Yes. This is particularly vital when attempting to wash in hot water.
Why is hot a variable? Doesn't the water heater simply provide boiling water?
It provides hot water, but the maximum temperature is artificially capped. Modern residential water heaters are almost universally factory set to a maximum of 120 degrees Fahrenheit as a strict safety measure to prevent children from scalding themselves at the tap.
Oh, of course.
So the machine's FTC definition of a hot wash requires 130 degrees, but your house physically cannot deliver water hotter than 120 degrees.
So the hot setting on the machine is making a promise it cannot physically keep.
Furthermore, when you select the warm setting, the machine's internal valves simply open both the hot and cold lines equally, mixing them 50-50.
Okay, do the math for me.
If your hot water is capped at 120 and your winter cold water is 40 degrees, the resulting 50-50 mix yields a warm wash of exactly 80 degrees.
Wait, really?
Yes. You believe you are using warm water, but you are barely clearing the threshold for a cold wash. The dial on the machine is essentially lying to you based on the physics of your basement plumbing.
That fundamentally changes how I view the control panel. So thermal energy is one massive variable. The other invisible variable is the mineral composition of the water itself. Hard water.
Hard water is the silent destroyer of textiles.
The classic symptom of hard water is pulling a fluffy bath towel out of the dryer and finding it feels rigid, like a piece of stiff cardboard.
That stiffness is the physical manifestation of mineral deposits. Hard water contains high concentrations of dissolved minerals, predominantly calcium and magnesium. When these ambient minerals interact with certain chemical components in laundry detergents, a highly detrimental reaction occurs.
So how do you fight it?
To combat this, households use water softeners, which fall into two distinct chemical categories: precipitating and non-precipitating.
Walk me through the chemistry of the two softeners.
Non-precipitating softeners, which often utilize complex polyphosphates, are chemically elegant. They bind to the calcium and magnesium ions and hold them suspended in a clear, invisible solution. They neutralize the minerals without creating any solid byproducts.
Okay, that sounds ideal.
Precipitating softeners, such as traditional washing soda or borax, take a brute force approach. They chemically react with the hard minerals to form an insoluble solid compound. They literally precipitate a cloudy, solid particulate out of the water.
And where does that solid particulate go? It doesn't just vanish.
It coats everything. It coats the stainless steel drum of the washing machine, and most devastatingly, it coats the microscopic fibers of your clothing.
Oh, no.
That stiff cardboard feeling on your towel is an actual microscopic crust of mineral rock bonded to the cotton. It causes vibrant dyes to look cloudy and faded, and as the fabric flexes during wear, those rock-hard microscopic deposits actively grind against the threads, accelerating the structural failure of the garment.
If I have a set of expensive bath towels that have already succumbed to this, they're stiff, they're cloudy. Is the damage permanent? Must they be discarded?
The damage is entirely reversible utilizing basic household chemistry.
Okay.
The source manual details a highly effective rescue protocol. You require a large basin. It must be plastic, not reactive metal. Fill it with 1 gallon of very hot water and dissolve 2 cups of plain white vinegar into it.
Just normal vinegar.
Yes. Submerge the stiff, crusty towels in the solution and let them soak for 15 to 20 minutes. The white vinegar is a mild dilution of acetic acid. The acid targets the alkaline mineral bonds of the calcium and magnesium crust, actively dissolving the rock back into a liquid state, stripping it away from the cotton without harming the cellulose fibers.
A bottle of cheap white vinegar chemically breaks the mineral bonds and rescues a $50 set of towels. That is practical alchemy.
It really is.
So we have audited our water temperature, we understand our mineral content, now we face the actual sequence of loading the machine. The source material places massive emphasis on the first 5 minutes of the cycle.
The physical sequencing of loading the machine is where the vast majority of consumers introduce chemical errors. Consider the standard behavior. A person throws the dry pile of clothes into the empty drum, pours a heavy capful of concentrated liquid detergent directly onto the dry fabric, and then pulls the knob to start the water.
That is the exact choreography of almost everyone I know.
And it is a recipe for chemical damage.
Why?
Modern liquid detergents are hyper-concentrated cocktails of aggressive surfactants, enzymes, and optical brighteners. Pouring that raw, undiluted chemical directly onto dry fabric causes immediate, severe localized absorption.
It just soaks right in.
The chemicals aggressively attack the dyes in that specific spot, resulting in permanent, faded chemical burns on the garment.
So what's the correct way?
The correct sequence is rigid. You must start the water first. As the drum fills, add the detergent to the water. Allow the mechanical action of the agitator to fully dissolve and uniformly disperse the detergent into a safe, homogeneous solution. Only then do you introduce the clothes, dropping them loosely into the prepared chemical bath.
Water first, then the chemistry, then the textiles. What about the introduction of chlorine bleach? Does that just go into the water with the detergent?
Subjecting your clothes to chlorine, bleach, and detergent simultaneously triggers a microscopic chemical war in the water, and the bleach always wins.
A chemical war.
If you are utilizing liquid chlorine bleach, you must wait exactly 5 minutes after the mechanical agitation begins before introducing it to the drum.
Why is a 5-minute delay critical?
It comes down to the specialized nature of modern detergents. A high-quality detergent is packed with complex, engineered enzymes proteases to break down blood and grass, amylases to digest starches. These enzymes are biological catalysts designed to hunt down and digest specific stain molecules.
Okay.
Chlorine bleach, specifically sodium hypochlorite, is a blunt, indiscriminate oxidizing agent. It is highly aggressive. If you dump the chlorine bleach into the water at the exact same moment as the detergent, the bleach instantly recognizes the complex enzymes as organic matter. It attacks and destroys the enzymes before they ever reach the fabric.
Wow. You are paying a premium for engineered enzymes and then instantly murdering them with bleach.
You neutralize your own expensive detergent. By allowing the detergent to agitate alone for 5 minutes, you give the enzymes the necessary time to latch onto the soil, digest the proteins, and lift the dirt into suspension.
Amen.
Once the delicate enzymatic work is finished, you introduce the chlorine bleach as a secondary wave to indiscriminately sanitize the water and optically whiten the fibers. Advanced washing machines feature automatic bleach dispensers specifically engineered to delay the release of the bleach for this exact chemical reason. But if your machine lacks that feature, you must monitor the clock and add it manually.
It is a masterclass in staving chemical reactions. The enzymes prep the battlefield, the bleach finishes the job. Once this intense chemical and physical extraction is complete, the machine must rinse the garments. Given the complexity of the wash chemistry, does the rinse cycle require warm water to successfully extract the suspended dirt and soap?
Thermodynamically, no. The source material confirms that a cold water rinse is highly effective and almost universally recommended.
So no need for heat on the rinse.
The primary function of the rinse is hydraulic flushing, displacing the contaminated wash water with clean water. Cold water accomplishes this perfectly while locking the synthetic fibers back into their rigid state and saving a massive amount of electrical energy.
Are there any exceptions?
The only noted exception involves individuals with severe dermatological sensitivities. If a person requires absolute certainty that every microscopic trace of surfactant has been eradicated from the fabric to prevent a skin rash, a warm water rinse provides slightly more thermal energy to break down the final, stubborn suds. But for the vast majority of loads, the cold rinse is the optimal, efficient finish.
Let's synthesize the journey we've undertaken today. We initiated this deep dive looking at laundry as a brutal physical burden, a chore so physically destructive and exhausting that aristocrats shipped it across oceans and 19th century households dedicated an entire miserable day of the week to survive again.
It's incredible how much has changed.
Right. The automation of the washing machine eliminated the physical suffering, but it masked the complexity of the task. We now understand that doing laundry effectively is not a passive chore. It is an active intellectual exercise.
Absolutely.
It's the practical application of physics. Balancing centrifugal loads, managing fabric on fabric abrasion, and navigating the mechanical limits of horizontal versus vertical agitation. It is the practical application of chemistry. Utilizing surfactants to break lipid bonds, understanding the thermal activation limits of enzymes, neutralizing the calcium in hard water, and staging the introduction of oxidizing bleaches.
By internalizing that knowledge, by systematically sorting based on fiber vulnerability and dye stability, by preemptively attacking high-friction zones with concentrated chemistry, and by strictly managing the temperature and sequence of the wash, you transition from a passive consumer to an active custodian of your wardrobe.
And the financial implications of that are massive.
You cease treating your clothing as disposable. You save thousands of dollars over a lifetime by simply not subjecting your investments to the premature mechanical and chemical death of an improperly managed wash cycle.
You take a task that induces anxiety staring at a mountain of chaotic fabric and transform it into a highly controlled, satisfying process. You eliminate the casino element. You pull the clothes out of the drum, knowing exactly why they are clean, intact, and vibrant.
It does, however, prompt a really profound consideration regarding the trajectory of our domestic engineering.
What do you mean?
We have traced a clear evolutionary path from beating linens against rocks in a 17th century river to the steam-filled boiling vats of the 1900s commercial laundries to the microprocessor-controlled, gravity-fed machines of today. Yet despite centuries of innovation, the fundamental paradigm has remained completely static. We rely on water as a universal solvent, chemical soap to alter surface tension, and mechanical friction to extract the debris.
We've just engineered increasingly sophisticated methods of beating wet clothes with a stick.
Precisely. The provocative question is what the next paradigm shift will entail, particularly as global awareness of water conservation and energy expenditure becomes critical.
Will we even use water?
That's the question.
Yeah.
Will we eventually render the concepts of water saturation and physical abrasion entirely obsolete? It is entirely plausible that the future of textile care relies on nanotechnology woven directly into the synthetic matrix of the garment, creating surfaces that actively repel silica and sebum, rendering the fabric inherently self-cleaning.
Wow, self-cleaning shirts.
Or, alternatively, we may see the home washing machine replaced by a dry cabinet utilizing ultrasonic frequencies or targeted ultraviolet light bath systems capable of instantly vaporizing organic compounds and dirt at a molecular level without a single drop of water or a single tumbling motion.
A completely dry, light and sound-based extraction chamber. The concept of washing would become an archaic term.
It would relegate the centuries-old reliance on water, soap, and friction to the museums, completely redefining our relationship with our textiles. It is a fascinating concept to ponder the next time you are quietly folding a freshly laundered shirt.
It truly brings the historical perspective full circle. The next time you find yourself frustrated by the perceived inconvenience of spending 10 minutes sorting your hampers into distinct piles on a Sunday afternoon, pause and picture yourself standing on a wooden dock in 17th century France.
Waiting for the galleon.
Exactly. Imagine watching your favorite garments sail away on a massive ship for a 3-month voyage to the Caribbean, just to be scrubbed. And take a moment to be profoundly grateful for the complex, automated chemical magic sitting right there in your modern laundry room.